me start by saying that I don't speak Greek, so you're going to have to ask questions in English. I'm originally from Barcelona, now based in Madrid, but I cover the central and eastern part of Europe, working in AWS with Arpit, that he came with me. He helps me covering this market, so if you have any questions, feel free to reach out to him as well. I joined AWS in September 2020, so last week was my 3-year anniversary. And now, I work as the specialist solutions architect for what we call flexible compute, which is the domain in which essentially, we cover a subset of AWS services. You know that we have plenty of services. We don't specialize in everything. We specialize in mainly EC2. So EC2 on demand, EC2 Spot, auto-scaling groups, capacity reservations, reserved instances, savings plans, Graviton, and then of course any AWS service that has an integration with Spot instances. So AWS Batch, ECS, EKS, EMR, and I'm sure I'm forgetting some, Beanstalk perhaps. So if you're using any of those services to run your workloads, we are the guys to ask as well. In case you don't know, Amazon or AWS in this case is well known for 2 things. One is being very customer obsessed, and secondly, being very data driven. And this translates into a customer satisfaction survey that I have prepared for you to fill at the end of the session. So there will be slides at the end with a QR code. I kindly ask you to fill it with any kind of feedback that you have, regardless whether it's good, whether it's bad, because we use it to improve, to know if the session was useful to you, if you would like to hear about other topics, or you don't want to see us again in advance, which is totally fine as well. And there you will see that there's also a text box that you can use to say, hey, so I work for this company, have this kind of workload, I would like to know more about this and whatever, and we can reach out to you and organize a specialized session on another thing. So for today, what I have planned is an overview of different cost optimization techniques or tools that you can use to run your workloads on Amazon EKS. So we will cover in detail EC2 Spot, also how to properly use it with Karpenter. Do you know what Karpenter is? Does it ring a bell? Okay, to some yes, to some others not. Okay, that's good. We will also introduce Graviton. Graviton? Yes? Cool, better. And then we will close with Kubecost. I'll show you how you can leverage Kubecost to have a better understanding of your cost at the cluster level, pod level, namespace level, so different levels of granularity. Even though today's session is going to be focused on EKS, what Arpit and myself do is help customers to cost optimize their applications, driving diversification across instances, across compute options, across architectures, and also to increase resiliency using the same mechanisms. So as I'll be covering those focused to EKS or Karpenter today, there will be some foundation around diversification that you will be able to apply to any workload, regardless of the service that you are using. If you're just using auto-scaling groups, or you are just using EMR or batch, there will be some concepts that will resonate that you can apply to those workloads as well. So let's just start with EC2 Spot. I always like to start this session with a quick knowledge check. And the first one is, are Spot instances based on a bidding model? Could you say this is true? Raise your hand if you think Spot instances are based on a bidding model. Yes? No?
Not anymore.
Okay, good, fantastic. Not anymore since 2017, I believe it was announced in reInvent. Now, the spot price is set essentially by the fluctuation in supply and demand, is adjusted gradually and in a very steady way. So you won't see price fluctuations going up and down often and in a way that cannot be predicted. The second thing that we hear is that Spot instances are it's not EC2, or it's a specific set of EC2 instances that we don't take care about, that we have there in a corner having dust and that we offer at lower discounts. That's also not true at all. Spot instances are the same instances that you can acquire through other purchase models, such as on demand, that we offer at steep discounts compared to on-demand, because that's unused capacity that we have over-provisioned for you to be able to acquire different purchasing options. But since it's not used, we offered it discounted. But we're talking about the same hardware, so it's the same physical resources that you are getting. Then, we hear that a lot. So we hear from customers saying, hey, we use Spot, but we use it in our dev and test environments. We don't use it in production because, well, it's not reliable and this kind of stuff. So, I mean, it is true that the first thing that you might think about Spot, because, well, we have these interruptions and this kind of stuff that we will hear later, that might make you think that you cannot apply that in production environments, which is not true at all. Indeed, we have customers running 100% in production in Spot, such is the case of Skyscanner, because as I will try to convey today, if there is a set of good practices that if you follow, you can be sure that your workloads will be resilient and you will be ready to handle this kind of interruptions that, because of the nature that Spot instances have, can happen. So Spot instances can be applied, let's say, to any kind of workload, but that workload must be Spot friendly. And what we understand by Spot friendly is that the workload must be ready to handle those interruptions, right? As you know, like there's a 2-minute notice that when you receive, you know that after 2 minutes you will no longer have access to that instance. So your application must be ready to handle that interruption and save the state of your application. But that doesn't mean that the application cannot be stateless. If in 2 minutes you are able to save the state of your applications and recover it at a later stage, you have nothing to worry about. Next thing is, well, yes, this has been covered already, non-production workloads is used everywhere, right? What we can debate is whether in the environment where we are, what allocation strategy to apply to Spot instances, which we will cover later, but the same principle that we would follow to configure Spot for production workloads can be followed for non-production workloads, and if done correctly, can be as reliable as it is with on-demand. And then last thing is, okay, you have convinced me. Now, I understand that Spot is good, it can save me money, and it's also reliable, but more workloads are not ready for Spot, so how do I start integrating Spot in those workloads? Well, thankfully, as I mentioned, Spot is nothing more than a different purchase model within EC2, right? So all the services that support on-demand, that support on-demand, such as EMR, batch, etc., and so on, make it to you very easily to adapt your workloads to combine Spot and on-demand. So if you go for Spot, that doesn't mean that you have to go 100% Spot. Our services that allow integrating Spot allow you to define different strategies in which you can set different ratios or percentages between Spot and on-demand to run a base on a set of instances that you know that you are not gonna lose, and on top of that, scale with Spot to save costs and scale out. So this being said, currently in AWS we have more than 650 different instance types. And capacity is organized in what we call a capacity pool, which, as you can see in the slide, a capacity pool is nothing more than a particular instance type in an availability zone. And by instance type, we understand an instance of a family and a particular generation and a size. So for instance, M5 large. So an M5 large in availability zone 1 in Frankfurt, that's one capacity pool, sorry. So if we are talking about over 650 instance types and we're operating in a region that has 3 availability zones, that puts at our disposal more than 1,800 capacity pools for us to leverage. And I want to introduce this topic because we sometimes do meet with customers that tell us, hey, we're not getting capacity. Like we have configured Spot, we have configured on-demand, but our workloads are not getting instances. And then we sit with them and ask them, okay, like how many instances are you leveraging? And they're like 2. Okay, you can do better. Like we have a wide range for you to choose. And even though it might think that, you know, capacity is limitless, it indeed is not. So it's very, very, very unlikely that AWS runs out of capacity of all the capacity pools in all the regions, but it can happen that in a particular moment there is not capacity for a particular capacity pool. That's why it's important to try to embrace this instance diversity in our workloads. So in case we run out of capacity on one particular capacity pool, our workloads can shift to a different one and start getting capacity from there. Yes, so each of these capacity pools can be acquired following different purchase options. By default, or well, let's say not by default, but let's say imagine that we get a capacity pool using on demand. In this case, we could have, let me see, where is it represented? Sorry, it was here, but I didn't see the colors. 1 second. Yes, so there's a part that it's purple and the extending part that it's in white. So from a capacity pool, the purple part represents what in a particular moment in time can be acquired by customers worldwide as on demand, and the part that it's remaining, that it's unused, is what you acquire as a spot. But again, same hardware that you are getting. So more details on spot instances. Again, we have covered that it's the same hardware than on demand. In terms of the pricing, the discount can reach up to 90% compared to on-demand instances. On average, what you see, it's around 60%, ARPIT, 60-65, more or less. Okay, and then the interruptions, right? And this is where things start getting sketchy because everybody's afraid of interruptions. So by nature, spot instances can be interrupted with a beforehand of 2 minutes. And why is that? Because remember that on-demand will always take precedence. So imagine that at a point in time, you manage to get capacity of one capacity pool as a spot, but then another customer comes and wants to get that capacity as on-demand. What will happen is that we will send you 2-minute notice to inform you that, well, we won't tell you who has acquired that, but that somebody else is interested in getting that instance as on-demand, and therefore you have 2 minutes to gracefully shut down your workloads. So there is a signal that will be sent to you, that you have different mechanisms to handle. By default, I mean, you can use EventBridge to capture it if you want. EventBridge is this serverless event hub service that we have in AWS, which acts like a connector between all the services that you can use to receive events and create trigger actions. So you can configure a rule in EventBridge to capture the spot termination signal, and that alert that you receive contains the metadata information of the instance that it's about to be terminated, and you can use that to do whatever shutting process that you require. But also these signals are integrated in other services such as auto-scaling groups or managed node groups if you have used those. So you can configure those services to automatically take care of those signals to proactively launch a replacement instance when a spot instance is about to go down. So talking about interruptions, I have talked about the 2-minute interruption notice, that this one is reactive, right? So whenever the instance is about to be terminated, we get that, but there is another one, another signal that is associated to spot that is proactive. And that is the rebalance recommendation signal, which AWS emits when it detects that one of the instances that you are using has a higher chance of being interrupted by the increased demand in that particular capacity pool. Now, this is only a recommendation. Getting this signal doesn't mean that effectively your instance will be terminated, but there are chances of that. Good things about this signal is that it can arrive up to 10 minutes before, so you have eight extra minutes to do some stuff. But again, receiving that signal doesn't imply that your instance will be terminated. So again, something totally optional. And again, this signal as well integrates with auto-scaling groups, integrates with managed node groups, and so on, that you can use to launch a replacement instance when you get this one. And then, of course, there is the termination notice, which is 100% reactive. You can do nothing to change the beforehand in which it arrives. It's always 2 minutes, and once you receive it, you can be 100% sure that after 2 minutes you will lose access to that instance. So to reduce the chances of getting interruptions in your workloads, again, I'm going to refer to diversification. Why? Because if you try to get capacity or all customers go to use the same capacity pools, what's going to happen is that there's going to be an increased demand of that capacity, therefore the availability is going to go down, and if you start getting it on demand, you will start receiving interruptions. So the key here is to consider as many instance types as possible and to let the allocation strategy do the magic. Later on we will talk about what the allocation strategy is, but the key is to consider multiple instance types so that the allocation strategy picks those where the most capacity is available and therefore the lowest chance to get interruptions. And now, another questions that we do get often is, okay, how often do these interruptions happen? Like, is it every 5 minutes? There's no rule of thumb. Like, this first is something that we don't track, that it's not publicly available. So if you find a website claiming that it's predicting the chances of getting an interruption of a particular capacity pool, that it's completely false because we don't share that information. What we do see is that for workloads that follow the best practices in terms of diversification from different angles, 95% of them finish their workloads without getting an interruption. And this is the key. So if you diversify, your workloads will be safe. Cool.
Can I ask something?
Absolutely.
When you receive the termination signal, do you have the option to keep the EBS volume that is attached to the spot instance?
If I'm not mistaken, you can, yes. Yes, but let me double check after the session because I'm not 100% sure.
I also have a question.
Yes.
But it's not very relevant to the spot instance, but
Sure.
the cost optimization in general. Is the same rules applies with the capacity tools when we do reservations? And regularly when I do reservations, does it go from the spot capacity pool or from the on-demand capacity?
By reservations, you mean settings plans and that kind of stuff?
The setting plan is more agnostic to the specific instance type, but the reservation goes in the family. Does it span across pretty much?
Okay, yeah, now I get your question. Yeah, so the concept of, so the capacity pools are the same, right? And then you have different mechanisms to acquire that capacity. So you will always be accessing the same physical infrastructure regardless of the mechanism that you use.
So I'm not affecting any spot capacity pool that you on demand.
No.
So my guess is the priority is always reserved, then on demand.
Yeah,
then
exactly.
spot.
Already, if it's reserved, you are not even able to get it by on demand. Which that's the error that we call ICE, insufficient capacity error. I don't know if you've seen it ever, but it can happen that you try to launch an on-demand instance and there's no capacity, right? So yeah.
So I just want to clarify, like, there's no priority for reserved instances.
Mhm.
We just have one priority on
Have it.
demand.
Okay.
Reserved instance is more like a billing concept on
Yes,
top of
yes.
it. So it's not a separate priority. It just on demand has the first priority, and whether you have reserved instances at the back or not doesn't affect
So it's the probability of getting an insufficient capacity error is the same whether you have a reservation or not, right?
Yes,
Okay.
that depends on that.
So you don't have an extra priority.
There's capacity reservation, right? Where you can.
There are different kinds of reservations. So you can do reserved instances, then you can do on-demand capacity reservations.
Okay.
Is that the one you mean?
Yes.
Okay. But what's it out then with capacity reservations?
So if you have a capacity reservation, you're 100% sure that you.
Absolutely.
Yes.
Absolutely. If in the moment that you make the request succeeds.
Exactly.
Yes.
Okay.
Good.
I have another question regarding the diversification that you mentioned. Since we don't have any data on the capacity pool sizes, what's the suggested way? I mean, we know that probably the general purpose instances have bigger capacity pools, and if you want something with a GPU, it will be a really scarce resource. So how do you suggest going with the diversification?
I'll cover that in
Okay.
this slide.
I think that AWS has a table that says a termination percentage of each instance class. So it's like M6 has a 10% termination, T3 that has thousands of it has 95% of termination, of non-termination. So you just extrapolate the math from there,
Okay.
which actually makes sense.
Yeah, it's called the spot instance
Yeah, yeah.
advisor.
Yeah.
Okay.
So you can just see which instance and which region.
Yeah,
has what.
and there's many math, and you can just
I think it's a
extrapolate from
rolling 4 weeks or something.
Yeah.
average something.
yeah.
Okay.
But then there are some other tools that are dynamic, right? Such as the spot placement score. Who knows what the spot placement score is? Yes.
Yeah, I think the score is that's also attended in AWS documentation, and it says that the percentage that you can acquire capacity of each spot on specific region and availability zone.
Not exactly. So let's say that you have identified the instances that you want to use, right? But now you have architected your applications in a way that you have a multi-region environment, or not multi-region, like not necessarily spanning multiple regions, but you are flexible in the region in which you deploy your workloads, right? Now, the question is, okay, where am I most likely to get this capacity? So this is what the spot placements call will tell you. So essentially, it's an API call in which you pass the list of the instances that you want to use, and it will return a sorted list with a score that will go from 1 being the worst to 10 being the best, and that represents the likelihood of that region to be able to have the capacity that you want to get. So, well, I'm not necessarily going to follow the order since we're talking about this, but region flexible, again, doesn't mean to span multiple regions, because that, I mean, potentially could incur in additional costs, but if you design your workloads in a way that you are indifferent in the region that you can operate, the spot placement core is definitely a tool that you want to use if you are using Spot. We have already covered instance flexibility, right? So out of those 600 and more than 650 different instance types that we have available, consider being flexible across sizes. So one thing that is important to do is the bin packing, right? So being aware of how many vCPUs we were able to land, and based on that configure our applications, but also flexible about families, about generation. Obviously we will have preferences, and there are ways in which you can assign preferences to instances when you want to get it, but not because an instance for your application is suboptimal doesn't mean that you have to completely discard it. Always remember that your optimal choice might not be available, and it's always worse not being able to get capacity at all than getting our top second option in the list, right? Then, I mean, obviously availability zone flexible. This is something that I wish I didn't even have to cover, but remember that capacity pools are independent per availability zone. So in the same way that capacity varies from region to region, it varies as well from availability zone to availability zone. So if you're not able to get a particular instance type in an availability zone, that doesn't mean that in EC2 is not going to be available. So always, again, try to consider as many availability zones as you can in the region where you are operating. And the last one, I mean, seems trivial, but in the same way that capacity fluctuates from region to region, availability zone to availability zone, it fluctuates over time as well. So try to consider running your workloads in a time or in a moment of the day that it's less usual for other customers to run stuff as well. So try to avoid running stuff on peak hours. Cool, what do we have left? Yes, allocation strategies. There was a question. Because we have talked about being flexible about our instances, so identifying what instances can we use. But now, obviously, so let's assume that there are 200 potential instance types that we can use. But obviously, we're not going to have 200 instances running, or maybe yes, but let's assume that we have an auto-scaling group in which we want to run, let's say, 10 instances. It's enough for our workload. So the question is, out of those 200 instances, which 10 do I select? And this is what the allocation strategy allows us to do. So essentially, it's the algorithm that selects the capacity from the capacity pools that we have identified as potential candidates for our workloads. And there are different strategies depending on whether we're working with on-demand instances or spot instances. For on-demand, we have prioritized, in which essentially you assign an integer priority to the instances that you have selected, and the algorithm is pretty simple, right? So it will iterate over the priorities, and if it's able to land that capacity, then it will get it. But then also we have lowest price, right? So the allocation strategy will pick the less expensive instances out of those that we have selected. And then for Spot, we have again lowest price, but we have other two that are not available in on-demand, which are capacity optimized, and we have a new one. I mean, well, maybe it's not new anymore since it was launched already some months ago, but still rather new, which is price capacity optimized. So let's see a comparison between the three. I'm only going to focus on the spot allocation strategy because the on-demand, I believe, are easier to understand. So if we had a workload configured with the lowest price allocation strategy, we have three different availability zones in the region where we are operating. There are different instance families, sizes available. Obviously, the lowest price allocation strategy will always pick the cheapest option. It's a no-brainer. If we configure it with the capacity optimized allocation strategy, then instead of the price, it will completely disregard the price and it will take a look only at the capacity. Pros of this allocation strategy, that it will drastically reduce the chances of getting an interruption. Cons, that it might not be the most cost optimal strategy. And this is why we created the new allocation strategy, price capacity optimized, which basically, and now it's the recommended approach. So we recommend using this allocation strategy for any kind of workloads, regardless of the service that you are using. So price capacity optimized takes a look at a combination of both price and capacity. So it aims at both reducing the number of interruptions and also decreasing the cost of running our workloads. So let me move over here. In availability zone 1A, again, well, this example is rather easy because for the R5 large, this is the instance family with the highest capacity and also the cheapest. So the allocation strategy will pick this one. For 1B, you can see that it would pick the R5 large because despite having less capacity, the price point is significantly lower compared to the M4 large. So we are losing significantly less capacity for the price that we are saving, then the allocation strategy will pick this one. And for, well, 1C, again, if there is the same capacity and one is cheaper, it will pick that one. Good. Yes?
Can you go back to the...
Absolutely.
Yeah, it works. So, that's the now recommended strategy, right? But doesn't that make it a bit worse for the customers because the price capacity ratio is always the same, right? The R5 will probably always be cheaper and more. It has more capacity than an M5 larger on an R6 or whatever. So it's first come, first served.
Well, first, why do you this thing about the ratio? I haven't fully understood.
Well, because when we get most people use the general purpose instance, right? The T3, T4, T3A, and so on and so forth. So, because now this is price capacity, and the price capacity for those instances is always the best, out of everything else, out of the I's, the P's, the R's, that means that they will always get taken first. So you have to work around that strategy by adding not commonly used instances, right?
But why would you see that as an issue if those got picked always? Which I don't know if it's true, but let's assume that it's true. Why do you see that as an issue?
Because when we have either the lowest price or the capacity optimized, right? We have a more specific pool to choose from.
But you want to avoid that?
I won't. But since it is now that recommended, and if someone doesn't change the allocation strategy, this will be picked up by default. Someone who is not well accustomed to using those strategies will probably be worse in the long run until he has pinpointed the exact capacity, the exact instance classes that I actually want. I want specifically an R4 or an M5 or...
Okay, yes, but so the allocation strategy won't select instances that you haven't considered. So when you configure an auto-scaling group, either you specify a list of instances or you specify a list of attributes that is dynamically resolved into a list of instances. This is what we call attribute-based instance type selection, which I'm not going to cover during the presentation, but happy to extend 5 more minutes and even do another demo of that. But if you are not selecting those instances, so the type that you mentioned that I forgot, if you are not selecting it, the allocation strategy will not even consider it.
I know, but you have to use different mentalities for each of those strategies because you will know how the other customers that want the capacity will react.
But
So it's
You
a
don't have to think about it. The
Yeah,
algorithm
exactly.
will take care of that.
correct. When you will get the optimal experience is when you diversify the farthest and when you use price capacity optimized. Because then naturally what is going to happen is that you will always have up and running an instance that is optimal from a price perspective and that it's also unlikely to be terminated. Obviously, if you only qualify, if only 2 instances qualify for your workload, using this allocation strategy, you won't change anything, right? But if you are considering at least 30, which is what we recommend our customers, that we tell them that they are well diversified when they are between 20 to 30 different capacity pools, which doesn't mean instance types capacity pools. Again, so it can be 10 different instance types across 3 different availability zones. When you do that and combine it with this is when you will max out your experience. Yep.
It really depends on your workload characteristics.
That's what I mean.
That will decide which strategy you're going to follow.
Yeah, well, I mean, obviously, if you are not multi-arc, all the Graviton instances you are not considering, but those won't be picked.
Yeah, we also tend to think of it as like a slider between cost and interruptions. So more than getting the instance, it's like losing the instance. So what you're comfortable between that slider, you just adjust it. So price capacity optimized somewhere like in between the 2 ends of capacity and plus price. So again, depends on the risk profile of your workload more than like getting capacity.
Yeah, exactly. So a key thing to take into account here is the startup time of your applications. Because even though a spot instance can be interrupted, you get a 2-minute notice and you can react to that signal in 2 minutes. So if in less than 2 minutes you can have a replacement instance up and running and your application has bootstrapped, you are not losing capacity. Right? Do you agree? But again, if your application has a slow start time, then obviously we have to consider another patterns, but for that we have warm pools or we have other strategies that we can implement. But besides spot and on demand, obviously there are other mechanisms for you to acquire capacity, such as RIs and so on. And the key is to combine all of them, because for some workloads, as you were saying, one purchase option might not be the optimal, but some others might be. So with RIs, we can set a base for our workloads in which we know for sure the demand that we will experience over time. And on top of that, depending on whether the workload is spot friendly or not, scale with on demand or scale with spot. This is just some example of how you could combine purchasing strategies in different kind of workloads. I haven't seen anybody taking pictures. You can, but I'm also thinking, well, there's a video, yes, but I'm thinking on sending the slides as well. I have no issue with that, so no need to take pictures if you don't want. Yes?
In an auto-scaling group, is it possible to mix different instance types?
Absolutely. You can mix and match anything that you want. Yep. Good. So we arrived to Graviton. What is Graviton? Let's start with a bit of history. In the beginning, in AWS, you were only able to run workloads on instances that follow the x86 instruction set. Then when AWS partnered with Apple, you could run your applications on ARM64, but through the Apple M1 processors. And now you have an extra option with this Graviton powered instances. And Graviton is nothing more than an ARM64 based processor that has been engineered by AWS to offer diverse price performance ratio for a wide spectrum of workloads. So in average, what we see is that it offers up to 40% better price performance compared to similar instances, and it's 20% less expensive than comparable x86 based instances, and also 60% more energy efficient. We're already in the 3rd generation of Graviton powered instances, and the 3rd generation, on top of the advantages that I already mentioned, offers 25% better performance compared to Graviton 2 powered instances. Good, so what workloads are well suited for Graviton? Essentially, almost anything, right? So from microservices to databases, gaming, web servers, stateless applications. At the end of the day, it's an EC2 instance with a different processor. If you are running containerized applications and you are able to build multi-arc container images, it's another tool that you can leverage to build that diversification. And the good thing is that besides the non-managed way, so using directly EC2, there are some managed services that offer a Graviton alternative. Examples for that are the ones that you can see here, but well, ones that resonate well for sure, AWS Lambda or RDS. And actually, another question or very revisited topic with customers is, okay, I want to migrate to Graviton. From where do I start? What do I do? For this, we have an open source tool called the Graviton Porting Advisor, which is available to download through GitHub, and essentially you run it in your servers, and it will scan your applications, and it will look at things such as the libraries that you're using, binaries, dependencies. If you have assembly code, it will check if that assembly code is ARM64 compatible, and it will generate a report on the steps that you should make or that you should carry forward to make your applications Graviton compatible. But obviously, the easiest is the managed services, right? Just changing the deployment option. Good. So finally, we make it to the last section of the session, which is EKS and Karpenter. Before getting into Karpenter, Amazon EKS is AWS's managed solution to run Kubernetes in the cloud. We give you a fully managed control plane. And then on the data plane, you have different options to configure it. You can go the serverless way with AWS Fargate, and you can go the non-serverless way with either self-managed nodes or EKS managed node groups. All this using Amazon EC2. If you have worked with managed node groups, you must have seen or experienced that over time it's very unflexible. Or as you develop new applications, everything starts growing and growing, because this is not an AWS limitation, it's a limitation of cluster autoscaler. And the thing is that a managed node group cannot mix instances from different purchase options, different architectures, different sizes. So you cannot mix an instance that has 8 vCPUs with an instance that has 16 vCPUs. You cannot mix Spot instances with on-demand instances, and you cannot mix Intel instances with Graviton instances. So if you want to diversify, essentially what you have to do is duplicate everything. So if you have identified 10 instances that you can use, you have to create 10 managed node groups. And then if you want to double the capacity of those instances, again, 10 more managed node groups. And if you want to leverage Spot, 10 managed node groups more. So this is something that is very difficult to maintain, and that over time requires a lot of operations to leverage the latest tools. And with this premise is why Karpenter was born. And you have to see Karpenter as a gateway to leveraging the wide range of compute options that AWS has to offer. It follows a completely different approach towards scaling your clusters, because it doesn't work with groups at all. It doesn't think of groups. It doesn't work with auto-scaling groups, with any kind of group. It works with another of our APIs to provision capacity, which is the EC2 Fleet API. And the EC2 Fleet API, particularly in instant mode, which is the one that Karpenter uses, what it does is it performs an API call requesting for capacity. So in the same API call, it can mix instances from different architectures, different purchase options in different availability zones with different sizes. And the response of this API contains two things. It's a synchronous API, so you get a response within milliseconds. Karpenter gets a response within milliseconds. And that response contains the capacity that was able to be launched and the capacity that wasn't able to be launched because, there was not capacity in the specified availability zone. So within milliseconds, Karpenter analyzes that response, and in case there's missing capacity iterates with the second most optimal option. By default, with Spot, works with the price capacity optimized allocation strategy. This is something that you cannot change. And for on-demand, it works with lowest price. Has support for launch templates as well, which is what you should use. If you're using launch configurations, please start migrating to launch templates because you are already missing out on instances that you could be using. Good. So Karpenter, it's an open source project that is Kubernetes native, right? So there is a team in AWS that maintains the Karpenter implementation for the AWS cloud. And you can to use Karpenter, you don't necessarily have to be using EKS. You could have your Kubernetes cluster running on premises, and you can have Karpenter running in your on-premises environments as well, and use the AWS capacity to scale your cloud data plane. So how does Karpenter work? The first thing that you have to know is that it will only do something when there have been pods that were marked as unschedulable because there was not enough capacity. So if we want to schedule a new pod and it can be scheduled in existing capacity, that's a cube scheduler. Karpenter won't do anything in there. But if the pod is marked as unschedulable, is when then Karpenter will make a call to the EC2 Fleet API to get the optimal node for the capacity requested by the pods that could not be scheduled. So it will take a look at the scheduling constraints, such as topology spread constraints, node selectors, port affinity, anti-affinity, tames, tolerations, all these Kubernetes native things, and we'll take a look at the aggregate requested capacity. So how many vCPUs each of the pods needs, how much memory, any hardware requirements, and so on. And it will beam pack all these in an API call to ask for the optimal node to fit these pods. So, and by optimal, I mean the most, well, the smallest or the most cost-efficient option. So it won't over-provision capacity. Yes, so more details on the beam packing. Well, a visual representation essentially of what I have just said. So if we have 4 smaller pods, it might ask for a medium-sized instance. If we have just one pod, it will get maybe a nano instance. Or if we have one pod that requires, I don't know, 20 vCPUs, it will get a 24x large instance or 2x large instance or something like that. And obviously, we can control the instance where we want our pods to land using labels or anything, any mechanism that Kubernetes offers. So there is not a Karpenter particular way of scheduling that you have to learn. Everything that you know about Kubernetes, you can continue applying within Karpenter. So I started the Karpenter, well, the section about Karpenter saying that it's a gateway to leverage all the compute options in AWS Cloud, but it has some behaviors by default, which, if we don't override, are important to understand. So starting with the instance types that it will consider, it will default to everything except metal and GPU. So unless we tell Karpenter to consider those, it won't get capacity of those pools for our pods. How do we tell Karpenter to consider all the instance types? It's as simple as, later we will see where we put this configuration, but for the moment, I just wanted to see the syntax. So we would use the instance type well-known label, and there are different operators that we can use. We can use in, we can use not in, and some more advanced ones. So in this case, we are telling Karpenter that after all the instances that by default considers, we want to exclude M5 large. This is just an example, right? There's not a particular reason why we would want to do that. What else? When it comes to purchase options, by default only considers on demand. So unless we tell Karpenter to get Spot nodes, it won't do it. To tell Karpenter to consider Spot as well is as simple as writing these 3 configuration lines. So we will use the capacity type well-known label and use the in operator to specify 2 values, Spot and on demand. And the good thing about it is that if we include Spot, then Spot is always prioritized. So Karpenter will always try to get a Spot node before an on-demand node to reduce the cost of our workloads. What if I have some workloads running in my cluster that cannot land on Spot instances? You use node selectors, right? So you have mechanisms to prevent those pods running on Spot capacity. What else? Regarding the architecture, by default only x86. If we want to leverage Graviton instances, there is this arc label that we can use, and simply by specifying two values in this list, we will be including all the range of Graviton instances. And when it comes to availability zones, by default, it considers all the availability zones in the region where we have deployed our cluster. If we wanted to override that behavior, we would use the zone label to specify particular values for the availability zone.
Will Karpenter handling the termination signals as well of stock instances?
It handles the the termination it handles, the rebalance it doesn't. If you want to handle the rebalance, there is this open source project called the node termination signal, actually, that captures it, and through an SQS queue, it sends it to, well, it puts it in an SQS queue, and Karpenter consumes it from there. Yeah. Cool. What else? Yes. So we have seen different ways to configure the capacity that Karpenter can use, and this configuration we will put in a custom resource that Karpenter defines, that it's called the provisioner. And here in the provisioner, there are different things that we can specify. So besides a list of requirements for our instances, we can also specify different ways to terminate our nodes. In this case, we're using something called consolidation, which I will cover in detail in a bit. But there's also some configuration by which we can expire nodes or terminate them after they have been empty for a certain amount of seconds that we will specify as well in the custom resource definition. So in here is where we essentially configure the capacity that we want Karpenter to consider, in terms of architectures, instance types, sizes, families, availability zones, anything that you need. A provision is a YAML file that you create, you configure with a particular syntax, and you register to your cluster. You can have multiple provisioners to serve for different teams, different applications, because one good thing that provisioners allow you to do is to define limits in terms of vCPUs, memory, or anything that you want to prevent Karpenter for over-provisioning capacity using that provisioner. So you can, well, there are different limits that you can use to control that. By default, you must have at least one default provisioner, because if you don't register one provisioner, even though there are pods that were marked as unschedulable, Karpenter won't know what capacity to get. That's why it's important to have at least one provisioner. And if you configure multiple provisioners, you can assign weights to them. And so whenever a pod could be matched to multiple provisioners, which is something that you should try to avoid. So you should set your scheduling constraints in a way that each kind of pod can only be matched to a provisioner, because in this way it's way easier to predict the capacity that potentially will be created. But if that doesn't the case, you can assign weights to provisioners. So in that case, Karpenter, what it will do is iterate over the provisioners that have been registered in the cluster and that are a potential match to the pod that could not be scheduled. It will start with the provisioner with the highest weight, meaning the one with the highest importance, and it will get capacity using the requirements specified in that particular provisioner. Good. So with a single configuration file like the one that you have seen in the previous slide, you can end up having something like this: an EKS cluster, the autoscaling of which is managed by Karpenter, and the data plane of which spans 3 different availability zones. And in each of those availability zones, we have instances of different sizes, different architectures, different purchase options. This is totally impossible to accomplish with manager rules. Impossible. Imagine the amount of effort that it would take you to configure managed node groups to be able to diversify as much as what you can see in this slide. Enormous amount of effort. With Karpenter, it's simply this: 10 lines of code, not more. Super, super, super easy. Good. So we have talked about the scale out, about how we tell Karpenter to get what instances. What about the scaling? Like, how do we terminate our nodes when we don't need them anymore? Or how do we replace them for more optimal options when the nature of our workloads has changed? Let's start with terminating nodes. There are two possible configuration attributes that we can use. One of them is the TTL seconds after empty. This property, what it specifies is the amount of seconds after a node has to be empty to fully terminate it. So in this case, that it's 30, it means that after no pods have been running on a node for 30 seconds, Karpenter will completely terminate the node to stop paying for it. And then we can also set the TTL seconds until expired to force Karpenter to renew the nodes after this amount of seconds, right? So regardless of whether they are running pods or not, when this TTL is set, Karpenter will renew the nodes. This can be useful for launching nodes with new AMIs, to reevaluate the allocation strategies, in case you have updated the launch template and have updated the user data script, and so on. And then we have consolidation, which is a smart feature, let's call it this way, of Karpenter that allows the tool to make changes in the nodes to reduce the cost. So let's imagine that we had 10 replicas. Let's imagine that we have a consolidation enabled and that we had 10 replicas running, and after 5 minutes we only have 2 replicas running. What happens here? If we configure the TTL seconds after empty, it won't work because the instance won't be empty, but perhaps for running 10 pods we needed a 24x large instance. Now we only have 2 pods. Perhaps we could be using a medium instance, right? So that's what consolidation does. It will reevaluate the resource requests of the pods that are running, and it will detect whether the instance or the instances in our cluster are still optimal for the number of pods that are running. And in case that's not true, it will consolidate the workloads. And by consolidating the workloads, what I mean is that it can either delete a node or replace a node. So in the same way that than the TTL seconds after empty, if a node is completely empty, consolidation will also delete that node. But what happens when it's not empty? It can decide to replace the node. So it can replace the node when it detects that the pods that are running in that node can run in free capacity in the cluster. So there is another node that can fit 2 pods perhaps, and also a cheaper replacement instance. So in that case, it will spin up a smaller instance, and the pods that were running in the instance that we're consolidating will be evicted and will be scheduled into the newly instance.
Say I purchased savings plans or reservations. Is Karpenter aware about it?
You have to make him aware of it in the provisioner. So you have to tell him what particular instance families you have to use.
But then I'm kind of constraining the very use of Karpenter, right?
No. Why?
I mean, if I purchased for the single instance family reservations, then I would have to use this specific instance family all the time. So Karpenter is
good, but then what you could do is configure different provisioners, one with a higher priority to consider the instances that you have reserved. So to tell Karpenter, first always try to get capacity from here. If there is no capacity from here, then fall back to this. Yep.
Sorry?
Yes.
So I have two questions. The first one is that sometimes there are the degradations of EC2 or Fargate instances, right? So how does that work in conjunction with expiration time and empty time? Does it handle that? Because it usually happens between like 2 and 3 weeks, and maybe I have said that refresh the pods every 1 month or something, like for security or whatever. How will that handle it?
First of all, Karpenter cannot spin up Fargate nodes. It's always EC2.
Okay.
Yep.
Simple.
Exactly. And then, I mean, the degradation by default, it doesn't detect anything. What you can do is perhaps override the behavior by which the instance is marked as unhealthy. If you detect something, update that, because when Karpenter detects that an instance is unhealthy, then it will replace that. But other than that, my recommendation would be to use the TTL seconds after until expired. And now that I'm in this slide, important thing that I've forgotten. The TTL seconds after empty is mutually exclusive with consolidation. So we either enable one or we enable the other. When would we want to work with one or the other? For instance, for batch processing workloads, analytics, and this kind of stuff that we know that we launch a workload and after it has been processed, we don't have to do anything else, then TTL seconds after empty. Because after the pods have done their job, we don't need the nodes anymore. But for workloads that are constantly running and in which the demand changes over time, then we want to use consolidation. So for web servers and this kind of stuff, consolidation enabled is what we want. Because TTL seconds after empty is very unlikely to kick in, because at least we will always have one node running, otherwise we won't have a web server running. And consolidation, remember that happens at the provisioner level. So each provisioner is in charge of consolidating the nodes that it launches. This is not something that happens like at a larger scale in the cluster by Karpenter. It's always at the provisioner level. Consolidation is triggered in cycles of 15 seconds, and it is something that by default cannot be changed. So it's 15 seconds, and that's it. And in each cycle, Karpenter will consider all the nodes provisioned by that provisioner, but it will only consolidate one node in each cycle. So you won't see Karpenter terminating 5 nodes in each consolidation cycle and spinning up 5 other nodes in each consolidation cycle. And to decide what node to consolidate, it will do it in a way that it's the less disruptive as possible, which usually means the node that is running the less number of pods. Good. Yes, so in terms of consolidation, that's it. What can we do about observability? So how do we know that our cluster is performing as we expected, that our provisioners are good and this kind of stuff? Remember that there are several metrics that are available through Prometheus that then can later be visualized in a Grafana dashboard. And so in here you can take a look at like the consolidation cycles of the provisioner, the amount of instances that are spinning up, capacity if you are hitting the limits and so on. So if you want to have a closer look or know in detail what's happening in your cluster, this is the way to go.
I'm going to ask a question.
Yes, sure.
Ask it right now, probably. So can you cover how on-demand or spot instances are
Yeah,
consolidation?
good question, thank you. Okay, so Karpenter will never consolidate a spot node, right? It might consolidate an on-demand node over a spot node, meaning it will remove an on-demand node and launch a spot node, but not the other way around. So Karpenter will never terminate a spot node to launch on-demand, but it also will never consolidate a spot node over another spot node. So even though we are running a 64x large instance in spot, it won't consolidate it in a medium instance in spot, even if it could. The reason for this is the allocation strategy that it uses, price capacity optimized. So it attempts to maintain a balance between interruptions and price. If it was consolidating spot instances only based on the price, it could totally be negating the nature of this allocation strategy. That's why it doesn't consolidate spot over spot, because it respects the allocation strategy. Thank you.
Talk
Yes.
a bit about the kind of workloads are better suited for this controller, because at the end of the day you have to introduce another controller into your cluster. What kind of workloads would you recommend to use with Karpenter?
Oh, everything. Yes, it's a perfect replacement to cluster autoscaler. So if you're using cluster autoscaler, I'd consider migrating to Karpenter. It's not a matter of the workload. It's a matter of whether you have the time to invest in migrating. But in the long term, you will see a lot of benefits. Not only by cost savings, but also in the time that you will have to invest to maintain your current architecture. Because there's one thing that I haven't mentioned, but let me go back, but in the provisioner, in here, you can see that we're not specifying particular instance types. We are excluding instance types, or we're specifying instance requirements, but not particular instance types. And this has the benefit that in the future, when AWS adds new instances, if those instances fall under the configuration parameters that you put here, those will be automatically considered by Karpenter. So you are naturally building more resiliency and diversification without even realizing. So this is a configuration that you don't have to revisit over time if it works. You will be adopting more compute options without realizing. Whereas with managed node groups, you have to create more managed node groups. If there is a new instance type that you can work and you want to use it in 4 different sizes and spot it on demand, you have to create 8 more managed node groups. Good. So, yes.
Sorry.
No.
It also connects with the metrics. How does can you configure Karpenter to scale in or out based on metrics?
Absolutely. Yes.
And on which ones, like memory, CPU, custom cloud metrics? Can you do step pods, like based on this, like you do with Fargate, right?
Yes.
Like, target strategy, I think, is step targets.
Well, but there are two. So there's step scaling and target tracking.
Sure.
Okay.
What can Karpenter handle?
But this is not Karpenter. This is the horizontal pod autoscaler.
Yeah.
So in the same way that you configure that with cluster autoscaler, you configure that with Karpenter.
Correct.
So the only thing that we are doing here is taking out cluster autoscaler and putting in Karpenter. All the scaling configuration that you did before still applies here.
Okay, so you just put on the spec sheet of
No. So you
that's-
configure the horizontal pod autoscaler in the same way that you did.
Okay.
So Karpenter serves to specify the capacity that can potentially be deployed in your cluster to run pods. That's the only thing. You don't configure how the workload to scale with Karpenter.
So you do that directly into this.
Correct.
Great.
Correct. And then there was another thing that you mentioned that I forgot that was interesting. Yes, step scaling.
Yeah.
We recommend the usage of target tracking instead of step scaling for any kind of workload.
Okay.
Good. So yes.
Okay, I don't know if it's the right time to ask this question, but I see a lot of similarity to how Fargate works if we count the diversity of the instance types.
Mm-hmm.
Compared to Fargate, what is the performance of a new node joining the cluster versus starting a pod in Fargate?
I have a chart for that in 2 slides. Okay, so how do we work with Karpenter? Where do we install it, or what options do we have to install it? So currently you have two options. Well, it's installed using Helm. So it's Karpenter currently, it's a Helm chart that you install in your data plane, right? So because obviously on EKS you don't have access to the control plane, you install it in the data plane, and you have two options. So essentially you install Karpenter on Fargate nodes, or you install Karpenter in a high available deployment using managed node groups. So those are the 2 patterns that we see. So we have customers that deploy a small managed node group with 2 nodes, or with 3, one in each availability zone to run a high available replica of Karpenter. And then obviously, don't let a Karpenter handle Karpenter itself, right? So make it not see himself, because otherwise if Karpenter terminates its own nodes, you've lost all your scaling. So it's either that or on Fargate nodes. It's on the roadmap to have a managed version of Karpenter that will become ready in the control plane for you. So it will be like an add-on that you could check when creating the clusters, or at a later point when updating it, so you won't even have to take care of installing Karpenter. So the chart. This chart is extracted from a blog post that wrote an AWS hero. So this doesn't come from an official AWS blog post like written by a solutions architect or a specialist of any kind, but it's a trusted source. AWS heroes are trusted people. So what this chart shows is the result of the time it took to schedule an amount of containers in this infrastructure. So on EKS, managed or in different ways, right? So we can see that, there was one that outperformed the others because this one is pre-scaled servers. So the instances were already up and running. Like there was no autoscaler that had to spin up new instances. But then the second two fastest options are EKS with Karpenter, either IPv6 and IPv4. And actually you can see that Fargate doesn't do very well. So the scaling with Karpenter is the fastest, even faster than with cluster autoscaler. Here you have the URL of the whole blog post. Good. So, well, yes. I mean, obviously use for instances in your workloads. Allow for that. Remember that you can configure multiple provisioners for different applications, as in like, I don't know, you have an application that only supports ARM instances or that only supports x86, create a provisioner for that. Or you want to manage in a separate way the capacity that different teams in your organization are able to get, then create one provisioner for each team, assign different limits. And obviously all the Kubernetes native stuff that you know, you can still keep applying. So all the scheduling constraint mechanisms that you have been using still apply with Karpenter. And when it comes to having an understanding of your cluster usage, is when we will use Kubecost, which is a tool that is built on top of the how's it called? OpenCost initiative, which is open source. And the good thing of Kubecost is that it's free to use if you're running on AWS, so you don't have to pay for it. And Kubecost gives you detailed information of the cost of running your applications at different levels. So a cluster level, pod, namespace, even by labels, I believe you can filter. So almost the possibilities are limitless. And it works in this way. So essentially, it consumes information from different sources. So from Amazon Athena, it gets the AWS billing data, and then from Prometheus, it gets a bunch of metrics, and then the same from Kubernetes APIs. It uses all that to build dashboard like the one that you can see here. That not only, I mean, this is just one screenshot of the whole thing that you can check. That not only shows what you are spending, but also provides recommendations to cost optimize your workloads. This was it. So, I have created an EKS cluster that has Karpenter installed in a managed notebook, and so we are going to scale the amount of replicas of a particular pod to see how it reacts. So to see how it does it, I have this view, which is, this is Kubecost view. Were you familiar with this? So this provides a visual representation of your EKS cluster. So essentially, if I hover over, well, these boxes, these represent the nodes. So now it's telling me that there are 2 nodes in this cluster. For each node, it shows the daemon sets that are running in each node, and then the pods that are running in this cluster. So this, I do have to zoom in. I don't know how to. Yeah, okay. So you see, if I hover over it, in this case, saying that the namespace is Karpenter, this is Karpenter working in this node, and then on the second node, there should be a replica of Karpenter running. So this is the only thing that we have in our cluster. We don't have applications running. So gonna scale the replicas of a pod to see how it scales. Now, to do that, I have this provisioner that has consolidation enabled, and that it will place this label to all the applications. This is to differentiate it from the label of the replicas that are running Karpenter, so that it doesn't consolidate those nodes. And then in terms of the requirements, for the moment I'm working only with on-demand, because I want to show you what happens when I include Spot after. And also I'm excluding small instance sizes, just as an example. I'm setting some limits in terms of CPU and memory, and then this is AWS a specific configuration that it's available in the Karpenter documentation. So this has to be like this, and that's it. So essentially, we're specifying the name of the cluster that we want to scale, so that it's able to discover the availability zones and subnets in the region where it's deployed. Good. So now to scale the number of replicas, well, I have this deployment, which in the moment that I created it specifies a number of real replicas because I want to scale it manually to show you how it behaves. And then it's using a pos image of a container just to, show something. Like it's not an application that will be performing any magic. And in terms of the requirements, I'm specifying that it needs one CPU at least, and this amount of memory. So now to scale the replicas, I'm gonna do, for the moment, first I'm going to specify, let's say, 3 replicas, and then I'm gonna go back to the view. And so you can see that there have been 3 pods marked as unschedulable. And now Karpenter will aggregate the requests of these pods. So the 3 CPUs that we specified will multiply it by 10, the same for the memory, and we'll impact this into a request to get the optimal instance type to fit this into. So in a few seconds we should see that it is. It already spun up a new node in our cluster. Now all the bootstrapping process is starting, is registering the node in the cluster, and it will have, and you see it already scheduled the 3 new pods into our new node. So let's see what it brought. In this case, this is a X-large instance. You can see here, it's an AMD instance, X-large, and it should be on demand. We can see it here. Cool. So now I'm gonna scale to 10 replicas and see what happens. So we have the 6, yeah, it's fun to look at, right? So we have the 6 extra replicas. And now it can happen that some of them can fit into the instance that was previously launched, some others might not, and therefore Karpenter will create a new one. So yeah, you can see now it launched a 2x large instance, and let's see how many of these go to this instance and how many fit in the other. Okay, so all of them went to the new instance. Now we have 10 replicas running. So I'm gonna scale down to 6. So you can see that there are 4 replicas that have been marked for deletion. And now what's going to happen is that we will have an over-provisioned node, right? So we will have a 2x large instance for just 3 replicas, whereas an x large instance is enough to run 3. So now consolidation should kick in and should either these three, put them here. Okay, this is what it's doing. So it removed the x large node because the 2x large is big enough to fit them. So it evicted them and it scheduled them into the new node. So this works for small amount of replicas, but I can also do, hey, I want to scale to 100 replicas. Now this will go like crazy. I don't think it's gonna fit in the screen. So we have all the replicas here pending to be scheduled. And let's see what node Karpenter brings. But as you can see, I mean, the node should appear in few seconds. So the scaling is really, really, really fast. So we're talking about 100 replicas.
Question about the previous step. I have a question about the previous step. Did it just terminate the node, or does it do it gracefully? Like it drains the node?
No, it drains it. Yeah. So it cordons the node and then drains the pods. Yeah. Good. So all of them went to the same instance. Why did all of them went to the same instance? Because we didn't set a cap for the maximum amount of vCPUs that we want to use, right? So in this case, if I zoom in, let's take it a look. So it's a 24x large instance. How many vCPUs does it have? 128, I believe. Probably more. Yeah.
96.
Good. Thanks. Yeah. 96.
You did
Yeah.
say 1,000 CPUs.
So now let's do one thing. Let's modify the provisioner to include Spot as well. And then, so we want to modify the amount of replicas. Let's leave it as it is, but let's see what Spot instance it brings.
Can I have, so based on the consolidation strategy, if we now set the pod size to like, I don't know, 60, how will it handle it? Will it terminate that graciously and open up maybe a 8 extra large or a 4 extra large? So
that will apply for the replicas that you launch from that moment, but not for the ones that have already been launched. So the resources requested by these pods have already been set. Or wasn't
okay,
that?
so we downsize, so we scale down.
But the number of replicas or the requests of...
The replicas. We
okay.
have 100 now, so we scale down to, I don't know, 60, 50, 40.
Let's do it. Yeah. What do you think it will happen?
From what we said earlier, it will probably spin up a smaller cluster because it's also on demand, so it won't have issues with Spot, and it will slowly migrate the pods to that instance.
So scaling to 50,
Yeah.
half of them gone. We're still in our 24x large, which now it's suboptimal. So again, it will consolidate these pods into a cheaper replacement option, which we can wait to happen. And then we will allow for Spot as well and see another consolidation cycle.
Yeah, I might have missed it. What is the bottom and what is the top?
Yes, so these are daemon sets and these are pods. So this is stuff that is running in the background 24/7. As you can see, these don't prevent for the node to be evicted or terminated. Those are not taken into account. It's only the pods that Karpenter considers. And one thing that I didn't mention is, okay, so what happens, I have consolidation enabled, but there is this particular node that I don't want to be terminated or something like that. So Karpenter, there are two things that Karpenter will always respect, which are pod disruption budgets. So if you set up pod disruption budget to have a minimum amount of pods running at any time, Karpenter will respect that, even though it's trying to consolidate the workloads. And also pods that you launch with the do not evict annotation, Karpenter will...
Low battery. It makes sense.
It will, no worries, it will. Oh, 4%, okay. Karpenter will consider the do not evict annotation as well, so it will respect that. Okay, so let's do the last change fast. I'm gonna open the provisioner, and what I had on demand, I'm gonna do Spot as well. I'm gonna save it, and now I have to register it again in the cluster. I have the cheat sheet here. I don't remember the command. Okay, it is. So I'm going to register it again in the cluster. Good. So it's being configured. And now, even though we are not changing the amount of replicas, we are telling the provisioner that it can launch Spot nodes as well. So these on-demand nodes that have already been launched, well, now it's only one, the 16x large, that it's an on-demand instance. Now it should be consolidated into a Spot node. And perhaps the Spot node into which is consolidated is larger. So maybe now it launches a 24x large instance, but since it's cheaper, it's going to consolidate it into that node. So let's wait a few seconds. Okay, there it is. Okay, and indeed now brought an 18x large instance, so a larger instance size. But you can see now that this is a Spot node. That's why it's going to consolidate into Spot, because despite being larger, it's less expensive. So the other node is gone already, and the bots have been scheduled into the network. And this is Karpenter in broad strokes. Hope you enjoyed the demo.